Okay, so here is a problem I quasi-invented to match up with another problem that we're going to do in a separate video. So I wanted to do the velocity triangles, or have an example where we did velocity triangles. So I created an impeller that looks like this, that has an outside diameter of 7.5 inches, an inside diameter of 3.5 inches, and an inlet angle here of 50 degrees and an outlet angle of 22.5. The thickness is the same, both the inlet and the outlet, of 1 inch. So that's the dimension out of the page. I have it running at 3,550 RPM and producing 320 gallons per minute. I decided, just because the other problem had this, as 140 degree Fahrenheit. So here is the specific weight of this fluid. And we want to estimate the ideal head produced and the hydraulic horsepower. So I don't like writing in, I guess I'll do it in black, in PowerPoint, so I'm going to use OneNote here. Okay, so if I will go ahead and convert, or just take my density, I'll divide by gravity, so I get 1 point. Ooh, this is not correct. Is that going to be wrong? I should have fixed this, but all my numbers are going to be wrong. Is that true? I think just at the end. I think I could change this and fix it. Okay. But anyway, I wrote down 1.94. I wish I had fixed this. Let me pause. I'll fix it. I'll fix it. I'll fix it. Okay, so that was easy. There's only one off. Okay. So let's see. The first thing I'm going to do, I'll convert my volumetric flow rate from 320 gallons per minute into cubic feet per second. So that's 7.48 gallons per cubic foot, 60 seconds per minute, 0.7130 cubic feet per second. I'll convert my angular velocity, so 3,550 revolutions per minute, multiply by 2 pi radians per revolution, divide by 60 seconds per minute, and we end up with 371.8 radians per second. I'm just writing down, I guess, because we're given OD and ID. So let's get our R1, that's the inlet, so that's going to be 1.75 inches. We'll turn those into feet. And R2 is going to be 1/2 of 7.5, which is 3.75. And in terms of equations, we will want to have beta 1 was the, there's already wrote that, but I'll write it again. 50 degrees, and beta 2 is 22.5 degrees. Okay. So we can find what the normal velocity components are going to be at each of these spots by taking the volumetric flow rate and dividing it by the area around the perimeter. So we'll take V1, and is going to be volume flow rate divided by the circumference, 2 pi R1 times B1. So we'll take 0.7130 and divided by 2 pi, and R1 is 1.75 divided by 12. And B1 was 1 inch, so 1 divided by 12. And all the units will work out so that we end up with 9.338 feet per second. And in a similar manner, we take 0.7130 divided by 2 pi, and now we take 3.75. Should be 3.75, right? Looks like a 2.5. 3.75 divided by 12, and also 1 divided by 12. and we should get 4.358 feet per second. Now taking the equations we had shown in the previous video for the tangential components, we'll take the tangential component of velocity is going to be omega r1 minus v1n divided by the tangent of b1. So we have 371.8. We're going to get this in feet per second, so we're going to take 1.75 divided by 12, and we'll subtract out, let's see, v1n, which is 9.338, divided by the tangent of 50 degrees. And as I had mentioned in the previous video, we could have found an angle there where this would have resulted in 0, but we don't have that instance in here. We have 46.38 feet per second. And in a similar way, we find the tangential component here of the outlet, beta 2. So we take 371.8 radians per second, and we'll multiply it by the radius of the outlet, and take the normal component here and divide it by the tangent. In this case is 22.5, and we end up getting 105.7 feet per second. And we really wanted that because we wanted to use Euler's turbo machine equation, which we will write, and this is the ideal case, by the way. So we'll say the power, so they use subscript shaft onto here, but I don't think we should use that shaft. But anyway, so this is more like the ideal head. I'll call this ideal. Not thermodynamically ideal, but mechanically ideal, where we have density times omega times our volumetric flow rate, R2 times V2 tangential minus R1 V1 tangential. So here is where I use the 1.91 and my angular velocity of 371.8 and my volumetric flow rate of, where'd you go, 0.713, and my radius 2, 3.75 divided by 12, my V2 105.7 tangential, subtract out R1, which is 1.75 divided by 12, and times my V1 tangential, 46.38. And by the way, let me go ahead and I'll make a big division symbol there. 550, because everything here would have been foot-pounds per second, and this is foot-pound per second per horsepower, turned it into horsepower, and we get 24.17 horsey power. And as we often want to do, we also want to find the head. We can do all of the same stuff. I guess I went ahead and wrote it all out, but we could just go ahead and divide that by the specific weight and the volumetric flow rate. So we could say, well, we'll say that the ideal head here is just going to be the ideal power divided by gamma, and this, which is going to be the same thing as the equation that I had written down in the previous thing up here, right? So that's going to be the same thing as this right here. So you could just say, well, we want to have the 20 here. Well, I'll write it out again. Am I lazy? Sure. not that lazy. And it's kind of weird how they wrote that out, right? Why did they put the omegas in both? The omega's the same thing in both places. That's kind of dumb. I'm not doing that. I'm going to put it right here. To go R2V2T minus R1V1T. There must have been a reason for that. I don't know what it is. So 1, oh, not to get 1. Let's go 371.8 divided by 32.2. And then 3.75 divided by 12, 105.7 minus 1.75 divided by 12 times 46.38. So I end up with 303.1 feet. All right, so here's the two things that we wanted to find in that problem. In the next video, we're going to talk about some practical pump concerns, and we'll have an example, and I will use this same impeller. So what we did right here was really sort of I guess I just didn't do it completely, was a velocity triangle problem, right? Where we took, here's the velocity that took place because of R omega, maybe R2 omega, R1 omega, and then we had a relative velocity, one that came up like that direction, and then one that came up in that direction, right? And if you used those together, I don't think I have another color, you'd find a actual velocity coming at that one. This one's got sparkles in it. It's nice right there. Isn't that nice? And then from that idea, that's where we end up getting these equations right here, where we're able, with this motion and then the normal component, which I didn't draw in here. Let's see, I don't know what color I can use here. Let's try this guy here. That's the blue sky one, isn't it? Yeah. We have a normal component that we can find right in there. And that's what allows us, don't think we have anything left, to find what the actual tangential component is for both of those. That's what the process that we've done right here. So we have an idealized way of finding what kind of hydraulic power we have imparted onto the fluid. And also, that would also, another way of looking at that is how much pump head we've created. But we're going to go look at a pump curve for this in the next problem after we do a little bit of an introduction to this. So that's it for this problem.